good morning. This is Math 238, differential equations, and it's already 8:18 in the morning, and I'm the only one in the classroom. It would have been started earlier, but my computer has been incredibly slow lighting off. I was working on the computer over the weekend at a place that had extraordinarily slow Wi-Fi. It was a DSL line and lots of people were on it, and it seems like my computer is still operating at that mode, which I don't know why. But before I get started on this slide, I can't remember exactly where we left off. Well, first student may be coming in. Yes, somebody is here. I was talking to myself and not having a fun time of doing it. I'm having trouble with my system. It's moving so stinking slowly. And the issue this morning too, I had a class that needed to move rooms and I hadn't been able to get permission, and I just stepped in and said, look, go on and move. But today is the 30th. All right. And Marcus is here. Okay, a couple things before we get started. Finally, this has come up. And it's just moving so very slowly. I did get all of your things loaded on the Blackboard. Okay? Now, my question to you is, where did we leave off? Okay? Did we get through the syllabus? Were we on the research paper instructions? Okay, did I get to my locator card? Okay. All right. But while I'm here, I've got the syllabus up here now. I did want to point out a couple of things. This thing is so slow. Okay. I don't believe it was like this before. On the core competencies here, I think when I've taught this before, I found out that chapter 1 was important enough that we did need to go over that. Even though it's not first order differential equations, it does lead to that, and it talks about those. So we're going to do chapters 1 and 2. I'll give you a short, quick test after chapter 1. Then we'll move into chapter 2, which is your big chapter, and it'll take a long time to get through that, and then we'll do that one. And then after chapter 4, we'll have another one, and if we get into chapter 7, we will have one after that. I don't know if we'll get to chapter 9 or not. There is numerical method in chapter 2. We'll go over that in chapter 2, so we may not make chapter 9. I think I went over that part. So while I had it up, I thought I would notify you of that change in the syllabus. Now, I think there's one other. Let me go back to this. My office hours, and I'll talk about this again in a minute. I didn't know when I'd be leaving on Tuesday and Thursday. And when I put in my Monday and Wednesday long days that I have, my Tuesday and Thursday, basically, I'll be leaving as soon as I get through with that 3:30 class. Nah, okay, sorry. Back off of that. Officially, I'll be leaving then. Generally, I'll be here till 5. But officially, I'm not supposed to work more than 40 hours. And even with and I'll show you this on my locator card, so therefore I don't have any more official office hours after 10 to 12 on Tuesday, Thursday. But if you come by my office after 3:30, you'll probably still find me there, okay? Not every day maybe, but most days you will, okay? Now, let me also make this change. When we met last time, I thought my physical science class was going to make. When I met with the class, when I printed off the rolls and stuff, I found that only 4 students showed up, and there were only, 5 paid students. Okay, I said, I'm not sure they're going to run a course like this. I thought the 7 students that were in there, or 8 students, whatever it was, no, 9. There were 9 students, 5 paid and 4 unpaid. I thought they were going to let it run. I thought they were all paid until I ran my roll, and they weren't. Only 5 were paid, and then only 4 of them showed up. I said, I'm not sure they're going to run the course with only 5 paid students, especially since only 4 of them showed up, and the 4 unpaid students aren't here. If they were here, then that would indicate to me they're planning to pay. Since they're not here, I can't make that assumption. So they said, no, they'd rather not have the class, me go and cancel it. So I was in the process of canceling the class, and when I went by a registrar's office, 15, 20 minutes later, the lady in there said, did that student get back in touch with you? I said, what student? She said, oh, he really needs it. And that's what I asked him. Do any of you need it to graduate? Just like I asked you. And they said, no, we can take it in the fall, blah, blah, blah. I can take something else, and stuff like this. Fine, because it's sort of optional. It's not like this. Any science will do for them. But he got there and found out that the biology he had planned to take he couldn't do. The chemistry he had planned to take was a conflict. I mean, everything wasn't going to work. And then suddenly he found out he did need the class this summer. So I got on the phone with him. I really did need it. So I quit. I had already called the students and told those students and called the others that we're going to cancel the class. Well, then I had to call them all back again and say the class is back on, okay? So then when I went to do the roll on, I found out, entered grade attendance on Friday, we were only down to 8 students. One of the paid students was not there anymore, and he had been in class. So I called him up and said, you may not have gotten the message, but the class is running. He said, no, I already changed. I'm going to leave it the way it is. So he got his schedule changed. It was a different one. He got his schedule changed and said he wasn't going to change back. So I talked with my boss. He said, if a student needs it, we'll run it just like we do it this. So if that had been the case, I'd have had more office hours on Tuesday, Thursday, but now I'm back to fewer. And with that class in there, I don't have any on the after end. Okay. Now, about Fridays. I thought it was only last Friday and the Friday in August. Now I found out there's also this Friday. Even though it's in June, we're still required to work. I don't know why. I don't know the rationale for that at all. But as it turns out, with my long day tomorrow, and I'm probably going to be here pretty late today and more than likely Thursday, I'm not going to have a full 4 hours to give them on Friday. So I'm probably only going to be in the office an hour or 2. So I would say this Friday, 7:45 to 8:45. If I stay that long. I may stay longer, but then too, my wife, I told her that we'd be off this Friday, and she had already planned a trip up to Huntsville. Megan's here. So I won't be in the office. The offices will be open Friday, but I won't be there until 11:45. I'll probably only be there an hour. I know I've got to go over there for a little time, but it won't be very long. All right, I was just going over little changes I made in the syllabi since I gave it to you last time. We did finish going over the syllabus, didn't I? Okay. The other one, I've already talked about it. I'm recording it. You could go back and catch it if you wanted to. When I thought through it, the last time I taught the course, I had decided we really needed Chapter 1. Because to go into Chapter 2 without Chapter 1, I have to go back to Chapter 1 and refer to so much. So we'll have Chapter 1 and then a small test on that. Then we'll do Chapter 2, which is a huge chapter, and there'll be a test there. And then Chapter 4, we'll do that. That's a pretty big chapter. And if we have time, we'll do 7 and or 9. But the numerical methods we will hit in Chapter 2 and maybe a little bit more in 4. Okay, those are the only changes I know about the syllabus. Any questions that you know of. Okay, it's out there on Blackboard. You can see it, read through it. When you go to it, either print off that last page or just type in your name, type in the day, email me the last page. That lets me know that you've reviewed the syllabus, you understand it, you've had a chance to ask questions. If you run into questions while you're reading it, ask me the next day in class, and when you get those cleared, send me that last page. Okay, so I will end that. I thought I would. My system is incredibly slow this morning. It's having a hard time closing. There, it closed. Now, I think I'm going. Goodness gracious, I moved my cursor and the thing down here stays on this cursor. There, now it's changed. That's not what I want. This is what I want. There it comes. Since I had it up, I thought I'd go on and show you Blackboard. Y'all, I know you're familiar with it. Are you familiar? Okay. Here's our home page for this class. Okay. Now, this is the instructor side. Yours may look slightly differently, but it's going to be about the same. There's content. Under content is where you'll find all the things that I put there. They better be there too. I've opened it this morning to see, but because I did this over the weekend, and I was at a place where the DSL was so slow, and we had lots of people on it, so it was pretty miserable. My computer still thinks I'm there, I think. It's taking forever to do anything. Hello, come in. Content. Okay, click again. Okay, it's not responding. Let's try this. Let's see what in the world. Lawson State is not responding. It may not be my computer. It may be Lawson State. Let me try this again. Now it's come up. In a few minutes, Control-Alt-Delete will come up, but not yet. So here under content, there's the syllabus. We're just looking at it. Research paper instructions. Did we finish going over those last month? I thought we did. I told you it was going to happen. Okay. You're fine now. I'm fine. Cancel. All right. Locator card. Did I go over that? Okay. Let's go over that just because it has. I didn't have it done last Thursday. It's going to take forever to open, though. I hope it's trying. I thought it had sped up, but now I'm not sure. Let me try it again. Yuck. That's not what I went to. Okay. Let's minimize that. I'm sorry. Here's locator card. It will start shortly. If it does not, click here. I'm not sure what shortly means. My word, I would not have done this if I thought it was going to take this long. Open it. That's what I said to do, open it. So open. Okay, I am so sorry. The whole day runs so slowly. We've got to get some math before this is over with. What is this doing? while we're waiting for that to open, let's go on to the next part. Now, I don't have anything on the system for that except for sound. You can still hear the sound. Safety. Where in the world is this coming from? As far as you know, does this look like anything that could be malware, or does this look like something legitimate? Should I just X out? I think so too, because I'm in it. Okay. Again? Okay. You're right. Good deal. Okay. While it's still trying to open up. Safety. What 3 issues of safety do we need to worry about? Fire. Okay. Anything inside the building that would cause a problem. Let's start with the closest scenario, the one we hope will never happen, but it could. What if my computer blew up and it sets my papers on fire? What do we do? Okay, leave is certainly one thing we want to do, and let the whole building go down. We'll be safe, though, because we're out of the building, right? No. Okay, we need to do what else? Okay, we'll come back to that in just a second. All right. Maybe we do need to go over safety, okay? All right. All right. What else do we need to do? We certainly will leave, but what else do we need to do? Second? Okay, where is the closest fire extinguisher? That's certainly something we want to do, but really there is something more important than that. Again, we might... Yes, a fire alarm. Where's the closest fire alarm? Somewhere out here in the hallway? Yeah, not, okay? Because this part of the building, this is the second floor here, this part of the building was built way, way old back before the fire alarms were required in the building code. So nowhere on any hallway here will you find the fire alarm. Where you have to go is out this door here, take a left, go down that half flight of stairs right there, take a left when you get to the bottom, just past the restroom, there's a little corridor that goes across to the student services wing. As soon as you step there, that's the new part of the building. There's a fire alarm on this hall and that hall. So whichever one's closest, easiest to get to, there's one. So one of you, if not 2 of you, go to pull the fire alarm to notify others. Very good. Okay, then you said fire extinguisher, because it's here in our room, we'll try to take care of it before the whole building does. And I will take charge of that, but if one of you wants to get the fire extinguisher, where is it? Right there. Within 5 feet of where I'm standing. Right there is the closest fire extinguisher. Can't get much closer than that. Okay? So that's what one of you will get that. I'll take care of this. Then once one of you has gone down and pulled the fire alarm, the other ones, if you've gotten fire extinguishers, otherwise I will. What do we do from there? You said leave. How do we leave? Slowly, carefully go to the nearest exit. Now here's where the nearest exit is. You go out of the door, take a right, a left, you go down that short flight of stairs, half flight of stairs, take another left immediately, go down one more flight, and then head out of the building, okay? And where do we go? We head out of the building right here. This is our classroom up here. We head out right down there and head to that big parking lot right down there. Stay together. There's only 2 or maybe 3 or 4 of us. There is one person who's added to the class. He hasn't paid yet and he hasn't shown up yet, but hopefully he'll be here. That's where we go. And we stay there. Don't say, hey, no more classes today, I'm out of here. No, stay there. Otherwise, if we can't account for you, because once I finish trying to put out the fire and stuff, I'll grab my roll book, and I'll join you down there. And when I do, if I can't find you, then they'll come around and say, is everyone accounted for? I said, no, can't find Marcus. He's not here. Well, he must be back in the building. So someone will come in and risk his life or limb, his or her life or limb, trying to find you because you wandered off somewhere. You've been home or something. So stay together until we have that done. Okay. Otherwise, if it doesn't start here, then if you hear the fire alarm, we proceed out of the building. Again, I'll be the last one out because if anyone has trouble getting out or getting downstairs or something like that, I'll be coming along slowly to help. Okay, so that was the first. Okay, let's pause now since this has finally come up, and let's go to the locator card. Now this is, I've gotten this done. This just shows my summer at a glance here. I was telling Marcus, Friday for most of the term will be off campus. You know, the college is closed. But last week, I think after we met, I saw an email that they decided we will be here this coming Friday. Okay? But I'll show in a minute. I'm going to already have my 30 hours in because we're only having a 30-hour week because yesterday was a holiday. Is that right? 32-hour week. I'm pretty sure I have my 32 hours off before Friday, but I will come into campus on Friday, just probably for an hour or so. Okay? But anyway, let me show. Oh, and by the way, my name, phone number, and email, the same departments, mathematics, even though I teach physics. What's that? Okay, I will be there around 7:45 in the morning, Birmingham. But you need to see me Friday? Yeah. Usually I am on Birmingham campus on Friday. I've got to be there, I think, to sign something for my boss, my evaluation from last year. But if I can get that done earlier, I may not be on campus at all. And I'll explain that right now. Okay, now I can't get my whole schedule on here, but you got the general idea. Okay? My Mondays and Wednesdays are horrendous. Okay? I start at 8 o'clock in the morning. I'm here at 7:45. Start at 8, and I have 8 to 10:40. I have Cal 1, and then I've got 15 minutes. I'm going to try to eat half my lunch in those 15 minutes. And then 11 o'clock, Cal 2, and that goes until 1:40. And then in that 15 minutes, I'll try to eat the other half of my lunch. And then my Physics 201, and it goes through 2 to 3:40 to 3:50, which just gets off the page here, 3:50, but then immediately my lab starts, so I have 10 minutes in there between, that's to set up the lab, and I'll either be in this room, the first lab this way, or 259 down on the lower part there. And then as soon as that class is over, that lab's over, usually we'll finish labs a little early, then at 5:30, 202 starts. It goes until 7:20, but then at 7:30 that lab begins, and again it's in one of those three rooms, and that goes until 9 o'clock, so I'm off campus at 9. So basically, well, it's probably going to be more like 9:15. So basically I have 13 and a quarter hours minimum on Monday and Wednesday, as in tomorrow. That's 13, let's just say 13 hours now. Today, and Tuesday and Thursday, and I was telling Marcus this too, I had a real mix-up with my physical science class. First, I thought it wasn't going to make. The students said they didn't need it. We didn't know. I only had 5 paid students. But anyway, but Tuesdays and Thursdays, we start with this class. I'm here by 7:45. Start with this one. Goes till 10:50. I'm in the office from 10 to 12. And let me pause here for a moment. Well, I'll get there in a minute. At 12 o'clock, I thought I had my physical science class, and I thought I wouldn't have my physical science class. And then it turned out someone did need the class, so it's back on again. So it's a small class too, not as small as this one, but it's a small class. It looks like 8 students. So it runs until from 12 to 1:50, then 2 to 3:30 is allowed, and then after 3:30 I'm supposed to be off campus. I was telling Marcus I'm probably going to be here past 3:30 just about every day. For instance, today, as soon as this is, well, I'll get to that. Okay. I'll probably be here closer to 5 most days. All right. Wednesdays look just like Mondays. Thursdays. Today, here's a big difference. As soon as I'm finished here, as soon as we're finished here, rather than officers advising, because in the physical science class last Thursday, I met with them, only 4 students were here, 5 were paid. I thought 9 were paid, but only 5 were paid. Only 4 of them were here, none of the unpaid students, so that's why I thought we were going to have to cancel. And I first said, now if any of you need the course to graduate, we can keep it open, but otherwise, no, we don't need it, we can take something else, I can take it in the fall, blah, blah, blah. So we're going to cancel the class, and then later I found out that one student, when he tried to change to another science course, they were all either canceled or they conflicted with his current classes. So suddenly he needed the class. He didn't tell me that, so then we opened it, or we didn't close it, cancel it, and then I had to call students back. As it turned out, one of the students who was here, a paid student, changed his and didn't want to come back. So anyway, it was a mess. We didn't do anything in class on Thursday. So today, rather than starting and doing all this with the syllabus and stuff, I'm going to, right up here, stay in the classroom and finish doing the syllabus, the research paper, all that kind of stuff, and try to get all that done so in this afternoon's class we'll be able to start. Then, here at the end, when it says off campus, I'm either got to, at that point, do my contracts for the fall term because I'm on the department chair, or I've got to go to the Birmingham campus and do it. So, as it's going to turn out, today I'm going to be here way past 3:30, either on this campus or Birmingham campus. And then tomorrow I've got a 13-hour day, so let's just say I finish the day. As it is, this is 7:45 to 3:30. What's that? 7:45 to 12:45 is 5. 12:45 to 2:45 would be 2 more hours. That'd be 7. So I'm here 7 hours and 45 minutes. If I left right then, but as it is, I'm going to be here probably at least 8 hours and probably longer. So 13 and 8, that's 21 hours right there. And then do another, let's say 8 hours on Thursday, which I'm pretty certain I'll do at least that much. And I'm not going to have a couple hours to go before I've already done. So that's why on Friday I probably won't be on campus very long. Not that I'm a clock watcher or anything, but my wife's already planning. Well, we have a nephew who is graduating from high school, and there's a special thing going on for him at noon on Friday. And normally I wouldn't have done it, but my wife thought I was going to be off, so she's already committed us to be there. So I will be leaving probably around 10, so I may be on campus till 10. So there's my locator card. And very little office advising hours. These 2 1-hour blocks, all I got. I ate lunch in my office. You can come see me then too. I never take a full hour anyway. But I've got nothing on Monday, Wednesday, just a little bit on Tuesday, Thursday. And then, like I said, most Tuesdays and Thursdays, I'll be here after 3:30, so you can catch me then too. All right, any questions on my locator card? All right, and that goes over that as well. Since I'm going to use this later, I'm just going to minimize that. Let's go back to content. Usually I don't do this, but since I had it up anyway from working on it this weekend, so terribly slow. Move. All right, we talked about the syllabus. Research paper instruction locator card. The next two sites you see here are sites that either I found or students have told me about that they found useful in the course, or I thought you might find useful. And I believe Slater is the one that, where I was this weekend with very slow internet, very slow Wi-Fi, and lots of people on it. I don't know if that's the reason or Slater just doesn't have it. He doesn't have this new edition, or at least I couldn't access it where I was. So therefore, Slater has the old edition, but very little has changed. So if you can't get exactly what you find in here, you'll find something very, very similar there. Okay? Midnight Tutor is just, that's a different issue. And I've got the link to the MTH238 YouTube videos. Now let me tell you about that too, and since I'm here, I hope we can get there quickly. Just click on that. I can't tell if it's trying to respond or if I need to do a double click. It's not doing anything. Ah, here it comes. This takes you straight to YouTube. I'm not going to load it because that takes even longer. But I'll explain to you what's going on here. Okay. What you see at the beginning are things that are left over from 2 terms ago. Section 4.5 and 4.6. Okay? Those were sections we covered 2 terms ago. Okay? Then, beginning here, last term. This is last term. As I covered these 2 terms ago, I'd wipe those out. So those are there. Keep on going down. There's 1.1, 1.2, 1.3, 2.1, on down 2.5. Where is it? No, it's lost. Okay, there we go. 2.6, 4.1, blah, blah, 4.3. And you see last term we only got to 4.4. Part of the reason for that, we lost a week and a half of classes on Monday, Wednesday classes last time. So we didn't get as far, so that's why I left the 4.5 and 4.6 from the previous term up there. This, however, is where we began this term. So always go to the very bottom if you want what we've done this term. If you want to preview what we're going to do, then I've left these up here so you can look at those. Like if you're missing some classes or something like that and you know ahead of time, you can go back and get a pretty good idea of what we're going to do before. Like today, wherever we get now, I don't know if I'll supersede some of that, but certainly on Thursday, when we get into 3.1 or 1.1, we'll probably pass where we did there. So I'll start losing the ones. When I got the new terms here, I'll take off the previous term up there. Okay? And this thing keeps coming up. I don't know what this is. I'm afraid this is garbage. Does anyone know what this is? I refuse to open it, but it will not go away. I'm going to take my computer down to, it went away that time. Thank you. Before, it couldn't. I just had to bring something on top of it. Okay. So there is how you access. And I'm going to leave Blackboard Learn up, but let's go to this and let's get started. Let's get this over with. All right. Oh. Everything's so slow. Get started. There we come. It'll pop up one of these days. I mean, this is not a big file. It has one graph page and one blank page and then another blank page saying go back to the previous blank page. It's a 3 PowerPoint display, three pages, and it takes forever to load. It's already loaded. It's taking forever to change to that. I say go to current slide. There, it finally did. All right, we're ready to start, or I hope we are. All right. Whew. Any questions before we get started? All right. Chapter 1 is Introduction to Differential Equations, okay? And you have a book. Do you have one yet? Not yet. Okay, is yours this edition or the previous? Previous, I thought so. Okay. I don't think much has changed. But what's on Slater is that edition, not this edition. So, but nothing much has changed. The words differential, if you remember back to Calculus 1, we did derivatives where dy dx is equal to blah, 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 right? A differential is if you said something another dy is equal to or plus something another dx, that's a differential form. If you have the dy and dx separated, either on opposite sides of the equal sign or both on the same side, that's equal to something, but they're in line, not dy dx, but something another dy plus or minus or equal something another dx. Yeah. That was what we called a differential. Okay, so what do we do differential equations? Well, that would be like dy. Okay, derivative dy dx is equal to something. That would be a differential equation. Now, we're used to having the y first and then taking the derivative of it. That's what we did in Cal 1, right? Now we're going to be given dy dx, and you have to figure out what the equation was. Well, you might say, can't you just integrate? Yes, you can if, there's one condition, if those forms are separable. Okay, we'll talk about that a little bit later. That's the first thing we're going to try to do. Okay? But before we get there, we're going to see, and the books do this these days. Back when I took it, we didn't mess around with this, but because the book expects you to know it, I do need to take the time to do it. But let's first look at definitions and terminology. The derivative dy dx, okay, of some function y is equal to phi of x, okay, is itself another function. And we call that dy dx, and this is where derivatives have so many ways you can express them. Dy dx, if y is equal to that, when you take the derivative, let me do it over here. Okay, if this were Cal 1, we would say dy dx is equal to phi prime of x. That would be one way to write it, right? Or we could have said d phi dx. Okay, that's another way to write it. Okay, but what this is, this thing here, is just some expression of x, right? So if that's all you had, then that's what is called a differential equation. Okay, here's an example of it. In fact, here's a few examples of it. If your y here, if this phi of x in this case would have been e to the 0.1 x squared. Now, why they chose that one, I don't know, but it's perfectly fine. What would dy dx have been? If y is equal to that, what is dy dx? Cal 1. A little louder? Okay, did you say e to the, is that what you're saying? I can't hear. Okay, not quite 2e, 0.2e. Okay, right. Okay, let me, okay. I'll start over. 0.2 e to the 0.1 x squared, and we're missing something. X. Okay. Now, I guess I'm really old school. What I would have done with that was take the derivative of the first, of the main function, which would have been dy dx. Derivative of exponential function is itself e to the 0.1 x squared times chain rule then says take the derivative of the other, of the inner part, and that would have been the 0.2 x. And then I would have rewritten it as 0.2 x e to the 0.1 x squared, just because that's how my mind works, okay? If you see it to take the derivative first, do the chain rule part first, fine. It's going to wind up in front most of the time. But that's the answer, okay? Now, if that's where we had started from, dy dx is equal to 0.2x e to the 0.1 x squared, and I said what function y would give you that? Well, we know now, but what we would do is write it in differential form, leave the dy up here, move the dx over here, that's the differential form, integrate both sides, y is equal to, and you see this is a substitution. Let u be this, du would be that. Yeah, that's going to work as a substitution. Yeah, and you'd wind up with that plus c, because anything, that function right there, plus 17 minus 45 thirds plus pi 16ths, you take the derivative of it, those constants go away, so you would get that within a constant, okay? So that's how you would do that. Now, I jumped ahead there, not telling you that yet. Okay. Now, let's do something else to this. This part right here, what is that? That's what your y is. So you could also have written this dy dx is equal to 0.2 x y. Right? Now you look at that, and that looks totally different. I can look at that and say, yeah, I can undo that by doing, well, this is obvious, except we know where it came from, and you can do that. So this is what we call a differential equation. It's not really obvious how you get back to that. That one is. This one's not quite as obvious, but you know you get there the same way. Okay? So here's a definition. I know you got in yours. The equation that we use to come up with that, or this thing right here, this equation here, is called a differential equation. Even though it's not written in differential form, it's written in derivative form, that's what we call a differential equation. If it has either a derivative here equal some expression of x's and y's, okay, that's a differential equation, okay? Now, if it was written dy is equal to blah, blah, blah dx, that's also a differential equation in differential form, okay? And there's other ways you could write it as well. Let's consider a more precise definition. And since you don't have it, let's clear the page here. And by the way, I think I mentioned this to you last time. This text, which I've heard other people say is the best text for differential equations, what we teach at the two-year college system level, it has no PowerPoint. Or at least it didn't. This is a new edition now. I know you got the old one. No. I was just looking in the front to see if this new edition had PowerPoint, and I do not see it anywhere. Just make sure I'm not missed it somewhere. So I can't load any PowerPoint for you because they don't have any. So this is taking the place of our PowerPoint. So here's a definition. They call it definition 1.1.1. I don't think they called it that in the old edition. An equation containing, and I'll abbreviate like crazy people, an equation containing the derivatives now I'm writing this one out, the derivatives of one or more, I should have put in one plus, unknown functions, okay, like I said, I'm abbreviating, or dependent variables, okay, with respect to, WRT is with respect to, get used to that, you'll see that a lot, one or more independent variables, one plus independent variables, okay, is said to be a differential equation. And differential equation from now on is going to be a DE, okay, because I don't like to write. I wish they had PowerPoints, you could have it all here, but that's what we mean. Now, obviously, we've expanded this big time from what we had before. Why? First place, we said derivatives. That's why I wrote out the whole word here. Last one, we only had one derivative. We could have more than one derivative, okay? We have, because it says of one or more unknown functions. Before we only had one unknown function, y. Now this is allowing us to have more than one. So if we had a, say, y and a z both that were unknown functions, you could have a dy dx and a dz dx, both in there. You could have multiple of those. You could have second derivatives. You could have third derivatives. You could have mixed derivatives. You could have partial derivatives. Y'all both had Cal 3, right? You did partials. So this gets a lot more complicated. We're not going to do partial derivatives. We're only doing ordinary, okay? Now, this could be unknown functions or dependent variables. In our last one, the dependent variable is y. It was the unknown function v. Remember, those were the same. They were interchangeable. Okay. With respect to one, now last time we only had one independent variable. Which was that? X. The x was the independent variable. Y was the dependent variable. But now this definition allows us to have more than one. Let's say our independent variables were S, T, and R. Okay? And then we could have dependent variables of X, Y, and Z. You did that in Cal 3 too. So you could certainly have more than one independent variable. Okay? Then you would get into partial derivatives, but that would be a differential equation. Now we're going to deal with ODEs, ordinary differential equation, not partials. Okay? We will mostly, or at least start with first order differential equations like we just have, but later we'll move into second and higher order. So we're going to get into a variety of these differential equations, but this is your overall definition, even though this course is not going to cover all those. So we talk about, to talk about them, we classify differential equations according to type, according to order, and according to linearity. Okay? Now what do we mean by that? Let's take our type. I've just referred to them. There are two types: ordinary differential equations and partial differential equations. Partial differential equations, that's a higher course. Do that later. Now, are both of you engineers or any of you math? Engineering. You may still do partial derivatives. I was a physics major. We did partial differential equations. Some types of engineering live on them. What types are you? Mechanical? Second? Chemical. I think both of you will probably run into some partial differential equations, but in order to do it, either you'll pick it up in your engineering courses or you'll take a higher level math course, okay? You won't take it at the second year level, okay? It'll be a fourth year or graduate level. We're going to deal with ordinary. That means you have D's rather than partials, okay? So we're only going to deal with that. So that's what we mean by type, okay? So they do some examples here, and I want to go through these relatively quickly. If I could get my thing to come up, there it comes, okay? Here are some. I'm sorry. Okay. What type of differential equation is this? Ordinary, dy dx. That's what you look for. Doesn't matter what the other parts are, it's an ordinary differential equation. How about this one? Ordinary or what type is that? Ordinary, not partial, because there's no squiggly D, no partial in it. Those are still D's, not the little crooked things, okay? How about this one? Say that again? Okay, that means second order. Okay, so that's getting into the order part. See, I wish I had gone on and done all the definitions here, okay? This would be first order ordinary differential equation. Second order ordinary differential equation, okay? This next one, okay. Now this seems a little stranger, okay? Let's start this way. You got two types of variables. What kinds are they? You really have more than two, but the ones you know now. What type of variables do you have? Independent and dependent. Later, in fact, you may have already run into what you call intermediate. They're independent on this part, but dependent on that part. But these are, okay, now, can you find me, which did you say, what were the two types you said? Dependent, okay. What would be your dependent variable or variables in this problem? Okay. Yeah. Okay, what letters do you see on the board? Don't count the D's. Those are X, Y, and T. Now, of those, which of these are independent, which are dependent? Second? The independent is the T. You're absolutely, I don't know what you said, but I'm going. Okay. Whatever is down there, that's your independent. X depends on T, Y depends on T. That's why you can take a derivative of X with respect to T and a derivative of Y with respect to T. So these have only one independent variable, but more than one dependent variable, but that's still an ordinary differential equation. What makes a partial differential equation is if you have more than one independent variable. Okay? That's the key here. Up here, the Y was dependent, X independent. Over there, Y dependent, X independent. Because the X is in that denominator type looking thing, okay? Here, the only thing down there is a T, so that's your independent. These are both dependent. So that's still an ordinary differential equation. However, this is one that has two dependent variables. Okay? Now, how about this? And I mean, blatantly obvious. What type of differential equation is that? That's a partial, because you don't have these anymore, you have those squiggly things, okay? You call them partials, okay? Why do you have partials? You have two independent variables. So you only have one dependent variable, who cares? But you can take the partial of this with respect to the one independent variable and the partial with respect to the other. This happens to be a second order partial differential equation. Okay? We're not doing those. We're showing you those, but we're not going to do those in this course. Okay? But just so if you ever run into them, you can see them. Here's another. And these are just so obvious because of the symbology. I can't write. That's supposed to be equal. Goodness gracious, this thing is slow. So slow. Okay. Okay. Pretty obvious. What type is this? Partial. Okay. Now, this one you don't see but one end. I'm sorry, I got it wrong again. If I had written it right, you would see. Okay. Yeah. This one has two independent variables, x and t. Again, only one dependent. You could have more than one dependent, but you only have one in this case. But because you have two independent variables, it is. That's a second order partial differential equation. This is also second order. Even though it has a first order partial, you go with the maximum. Okay. So, and how about this one? Partial. Of course, it has the partial symbols. And it has two independent variables. Y here, x here. The equal sign doesn't care, but you have two dependent variables. Who cares? As long as all it requires to be a partial, two independent variables. Whether you see them or not, but we do see them, and those are partials. Okay. So in this first course, all we're going to do is ordinary. So why we spent that much time, I'm not sure, but I just want you to see there's more out there. Okay. Now, throughout this text, ordinary derivatives will be written by using either the Leibniz or Leibniz notation, which we've just been using, and again, hopefully you've run into this before, but if you haven't, quick review on this. The Leibniz notation, and since we're not going to mess with the partials, this is only going to be ordinary, you could have dy dx, d2y dx squared, d3y dx cubed. That's Leibniz notation. We can use, now if we were dealing with partials, no, don't do this. But since we're only going to deal with ordinary, we can use the prime notation. What would be the prime notation for the first one? Y prime, Y double prime, and Y triple prime. Okay. What do we do if you had a fourth derivative with respect to x? Okay, on that one you do this. Y, there's two ways you could do it. Parentheses 4. Okay? If you had a 4 there, you would think that's y to the 4th power. In parentheses, that means 4th derivative. I have seen some of the older texts did y to the IV. That means, because this you could think of Roman numeral 1, Roman numeral 2, Roman numeral 3, Roman numeral 4. I don't see that in many modern texts anymore, but if you ever see it, that's derivative. 4 by itself would be power, 4 in parentheses is derivative. Okay. We're not going to do too many with those, but in case you run into them, you got them. Now, if you were including partials, we wouldn't use the prime notation. Okay? Or if you use prime notation, you know you're not dealing with partial, you're only doing ordinary. And in partials, they have another notation which is somewhat analogous to the primes. It's the subscript. If that was a partial up there, you could write that as y sub x, okay? And then this would be y sub xx, and this would be y sub xxx. Because then, when you had more than one variable, you could have a y sub xt and a y sub tx and a y sub xt, yeah. So you could have, that would be someone, but since we're not doing it, forget about it, okay? Don't worry with it. But that would be the thing that would be analogous, or at least in my mind is sort of analogous. That keeps you from writing all those squiggly letters with the exponents and stuff like that. Okay. So what this allows you to do is write things a lot neater. You don't have up and down and that kind of stuff. And man, when you're making out tests, it's a lot easier to type those in than to do all those up and down. Okay, so what would this stand for? Y prime plus 5y is equal to e to the x. And y double prime minus y prime plus 6y is equal to 0. How would you do this in Leibniz notation? Okay, now, since you have this, this tells you x is your independent variable. This one, you don't know what the independent variable is. You just sort of have to guess that it's x, okay? But this one, this tells you this is your independent variable. So this would be dy dx plus 5y is equal to e to the x. This one, if they don't tell you, you just usually assume. Like in algebra, if they don't give you a variable, what's my favorite variable? X, okay. So this would be dy dx squared minus dy dx plus 6y is equal to 0. Now, if you knew it was a parametric equation, then usually t would be your independent variable. But if you don't know that, assume x. Okay. Usually it'll be pretty obvious. Okay. Now, I think we've hit most of the other stuff. Well, they give us another example of something I've already told you. X over dt squared plus 16x equals 0. Okay? What two variables are you dealing with? And which is which? Is the which? Independent and x is dependent. Very good. Okay. Now that is a very different equation from d2x over dt squared plus 16t equals 0. You work those very differently, okay? You're used to x up here being your independent, but don't look at this and say it's independent. It's not. It's dependent. So you have to look at your derivative to tell. Okay. Now, I'm not even sure I want to go into this, but you do see it occasionally. In fact, you used to see it in physics more. I don't think you'd see it much anymore. Newton, see, Leibniz used this notation. I don't know who came up with the primes. Euler came up with a lot of this stuff, so it may have been him. It could have been Gauss. Who knows who came up with it. But Newton used this notation because Newton was a physicist, and most of his derivatives were dealing with time. Not just a parameter t, time. So he would have written this equation as x double dot plus 16x equals 0. And that's sometimes called the dot notation, and some people derogatorily called it the fly speck notation, which was probably the big problem with it. A random dark spot on the paper might make you think x prime was an x double prime, so yeah, this is more obvious. That's obviously something that's there. This could be a fly speck, a bird dropping. I mean, who knows what it could be, but most people don't use that anymore. But if you ever see it, that's what it is, and it's used mostly, like I said, in physics when you're dealing with time derivatives. Okay. Partial derivatives use a subscript notation. We've already talked about that. I won't go into that anymore. So that's the classification by type, which really isn't much of a classification at all in our minds because we're only going to use ordinary differential equations. But remember, there is another type, and that's the partials. Okay? So let's now look at classification by order. Okay? I'm ordering you to look at no, that's not what we mean. Okay? Classification by order is what order derivative are you dealing with? And we've already hit on this. This is a first order, second order, third order, fourth order derivative. Okay? That's what we mean by order. Okay? Now, just to throw a little fly into the ointment here, I'm going to write one down and see if it confuses you. d2y over dx squared plus 5 times dy dx, that's a d there, to the third power minus 4y is equal to e to the x. That's not a 4, that's an x. Okay? What type of differential equation is this? Ordinary, of course. It has d's, not partials. Okay? What order is it? Okay, that's the trick. No, it isn't. It's only second. That's a second derivative of y with respect to x. This is a first derivative of y with respect to x raised to the third power. That's just a exponential, raising it to a power. This is an order, that's a first order raised to the third power. So, in just a minute, again, I wish they'd given me all the definitions and then had you look at it. This is a linear term because it's to the first power. That's a cubic term because it's to the third power. The next thing we're going to look at is the linearity of a differential equation. This one would not be linear because one of its, either the y or a derivative of y is raised to a power greater than 1. So this would be nonlinear. But it's a second order nonlinear differential equations because this is still a first derivative. So that's first order. And this is zeroth order. It's y. Okay? Your independent variable is x. That over there has nothing to do. If that had been e to the 17th, that wouldn't have been a higher order. Or e to the 17x, or anything, or x to the 17th power. Whatever good to the independent variable doesn't change the linearity. It's only the dependent variable and its derivatives. Okay. We haven't gotten there yet. I shouldn't have even mentioned that. Now, we will do some like this, and that's why they make a special mention of it. M xy dx plus n xy dy is equal to 0. What type of differential equation is this? Second, ordinary, because these are d's and not deltas, or whatever that symbol is called. Not really a delta. Del, I think, as some people call it, but that's not even consistent either. Now, what this means in front is you have some function of both x and y multiplied by the dx here, some other function of x and y multiplied by the dy there is equal to 0. This is called in differential form. That's derivative form. This is differential form. Okay? Now, we'll just leave it like that. We're going to do more with that later, and we'll have a special name for it. Okay? We're not going to bring that up yet. Okay? So, let's do example 2. If we assume that y is the dependent variable in the first order ordinary differential equation, then recall from calculus that the differential dy is defined to be, now this is this, dy is equal to y prime dx. Make sense? Because what's your y prime? Dy dx. If x is your independent variable, dx. Now, this is one of the toughest things about doing this is letting the notation assist you, but the notation isn't governing you. Okay? In other words, this almost looks like these cancel out. You have dy is equal to dy, doesn't it? Of course they don't. This is an operator here. That is not something that can be canceled out. But what it suggests to you is a good suggestion, that these two are equal to each other. Okay? We did the same thing, if you think about it, dy dx, and we've already done this, is equal to some function of x, right? And then what did we do? In Cal 2, we said dy is equal to alpha of x dx, and then we integrated both sides, didn't we? So we did the same thing of this. We wrote this and wrote it from derivative form into differential form, then we integrated and did, I've already suggested to you, that's one of the ways we solve differential equations. If this function is a function of x alone, then that's certainly what we would do. And you probably even did some of that in Cal 2 and maybe Cal 3. Okay. Now, let's start this way. Here, this is what example 2 is doing. Here's 2a. Y minus x dx, whoops, ahead of myself a little bit here, or I write sloppy one, I don't know which it is, plus 4x dy is equal to 0. This is one similar to that last form I showed you. Now, how can you, this is an equation, a differential equation, written in differential form. how can we write that in derivative form? And it really isn't very fair, but the book even says it. And we do it all the time. What's the derivative? Tell me what the derivative would look like here, or should look like here, in most circumstances. This is in differential form. What would be your derivative? Just the derivative. No. Just the derivative. If I said, okay, in this form up here, what is your derivative? dy dx. Okay? So that's what I'm looking for here. Now, how do you get that to look like a dy dx? Divide by dx, right? Okay, let's do that. Divide this side by dx, divide this side by dx, and of course we'll divide this side by dx too, but it's still going to be 0. These cancel out, you might say, and this gives you y minus x is equal to plus 4x dy dx equals 0. Okay? Now, most of the time we like to lead with the derivative form, so we just reverse the order there, and we do 4x dy dx plus y minus x is equal to 0. Okay? But if we're wanting your y's on one side and your things without y's on the other side, we write that as 4x dy dx plus y is equal to x. Okay. All right. That's how you'll typically see your differential equations. Okay? All your y's and derivatives of y's on this side, and anything without a y or derivative of y on the other side. That would be how you look at your differential equation. Okay? And that would be kind of a standard form of the differential equation. What started as this winds up like that. Now, will we do that every time? No. Sometimes this form is the easiest one to use, not that form. Okay? And sometimes we'll go from that form to this form. So, get used to doing that type of thing. I hate to do this, but I'm going to have to do a quick pause here. Here it comes again. These things keep popping up, and I can't get rid of. Oh, you couldn't see those. Oh, I had the projector on. Sorry, I forgot to turn the projector back on. That bike fence or whatever it was kept showing up again. So anyway, that's a differential form of a first order differential equation. And that showed you how you go back and forth between, or at least one way between. So let's do the other way. Goodness gracious, it's so slow. Dy dx plus x squared plus y squared is equal to 0. Okay? Now what it says here, that is in derivative form. Exactly. And what does that give you? This xy dy plus x squared plus y squared dx equals 0. There you have it in differential form. Really easy to go this way, and not too bad once you get used to it, and do it the other way. So you can go from one form to another in one section, we'll be doing this a whole lot. Okay? Now, this next, to me, always seems to give students a lot more problems. And I can see why, because sometimes it gives me some problems too. In symbols, we can express an nth order ordinary differential equation in one dependent variable by this formula. Now, I never have liked this form, but you can do it. F of x, the independent variable, y, the dependent variable, but also the function, y prime, comma, y to the nth. In other words, the nth derivative of y is equal to 0. Okay? Now, what's that say? Probably is not very instructive, but let's see. Where f is a real value function of how many variables? Independent variable. By the way, variable. N plus 1 variable. Okay? Now, it says for both practical and theoretical reasons, we shall also make the assumption hereafter that it is possible to solve an ordinary differential equation of this form uniquely for the highest derivative value, y to the n. So, like we just said, this form should be this, and let me just go up to y prime. What would your y prime be? Your y prime would be equal to subtract x squared, subtract y squared, then divide by 6xy, and then you solve that for that. Okay? So you could say, and using theirs, this y, the nth derivative would be dny x to the n, okay? That would be equal to some little l function of x, y, y prime, up to y to the n minus 1. Okay? other words, you can pull out what's that? Say this again. You're saying what? Yeah, we're not at the place of finding answers yet. Yeah, it's just how you're writing the question. Okay, let's take this one for instance. This one here, which we said could be written as in the capital F form of X, Y, and Y prime. Right? Okay? Equals 0. And that would be, they're basically in that form already. So your capital F is this function right here. So square the X, square the Y, and multiply the Y prime by 6.1. Now, what would that give you if you wrote it in this form? Here your maximum derivative of Y is just the Y prime. So that would be dy dx is equal to, the first thing would be minus x squared minus y squared divided by 6. So there you have okay. Now, when they write it like this, or like this, where f is a real valued continuous function, refer to that as the normal form of that thing. Okay? This, they don't really have a name for it. It's the capital F form, and this one will be the normal form of that. You pull out the highest derivative and you come up with a function little f of all the rest of it. So basically, anytime you have a dy dx, it's going to be some function of x and y. Independent variables, dependent variables. What would be your dy dx squared? What would be your normal form for that? What would be, no, for anyone. If you had any second order differential equation, you would have x, y, and y prime. Exactly. And this is all at the point you make it, or you think you've written those things, that you can write that. This next example we're actually, we're not, are we? I think we've done all the time. Sad to say. We'll start next time with example 2. Now, homework exercises here. That sounds like trouble. Really does. They don't have all odd number answers in the back, but they do have most of them. One example is really questions like that. So I think what you can do here is take the order and problem 1 states that take the order of the ordinary of the given ordinary differential equation and state whether the equation is differential. All you can do so far is just doing try to do 1 to 7 in the question you will do. Don't worry about getting this part. 1 to 7. I'm doing the odds, so there's no answers in the back for odds 1 to 7. very effective thermal insulation. All right, sorry we sort of, oh, the other thing I meant to tell you, I told Officer first, for the next little bit of time now, I'm not going to do a policy I'm going to stay up here because my first flight, took the fact that they decided not to have that, and then later when somebody had to have it, we didn't do anything that first. So I want to get, I got started Thursday afternoon, got the first part of the facility done, that took me what, almost finished the building, build it, the research station stuff, and the local